Tonight, as you prepare for sleep, let's travel to objects so dangerous that just getting close to them would mean your instant death. Dead stars spinning 700 times per second, black holes that stretch you like spaghetti, explosions that wipe out entire solar systems. Since the beginning of the universe, billions of years ago, these deadly forces have been out there dancing in the dark space. But here's the disturbing mystery in all of this. If the universe is so dangerous, how did life manage to appear? What protects us from these cosmic death machines? Tonight, as you prepare for sleep, let's travel to objects so dangerous that just getting close to them would mean your instant death. Dead stars spinning 700 times per second, black holes that stretch you like spaghetti, explosions that wipe out entire solar systems. Since the beginning of the universe, billions of years ago, these deadly forces have been out there, dancing in the dark space. But here's the disturbing mystery in all of this. If the universe is so dangerous, how did life manage to appear? What protects us from these cosmic death machines? Before we begin this journey into the most lethal corners of existence, I want you to settle in. Adjust your pillow. Let your breathing slow. Because tonight, we're not going to rush through space. We're going to drift slowly, quietly, past objects so extreme that they bend reality itself. And as we move through this cosmic catalogue of danger, perhaps you'll begin to appreciate just how remarkable it is that you're here at all, safe and warm, listening to these words. The universe is not a gentle place. It never has been. From the moment the first stars ignited, the cosmos has been filled with violence on scales we can barely comprehend. And yet, here on Earth, life emerged. Intelligence developed. You exist. How? What invisible shields protect our small world from the chaos beyond? These are the questions that will guide us tonight, but we'll approach them slowly, letting each idea settle before moving to the next. Let's begin with something strange, something that shouldn't exist but does, a dead star that refuses to be still. Imagine a star, not our sun, but something much more massive, 10, 20, maybe 30 times the mass of our sun. For millions of years, it burns steadily, fusing hydrogen into helium in its core, fighting against its own gravity with the outward pressure of nuclear fusion. It's a delicate balance, and it cannot last forever. Eventually, the fuel runs out, the core collapses, and what happens next is one of the most violent events in the universe, a supernova. For a brief moment, the dying star outshines entire galaxies. The explosion sends shockwaves racing outward at a significant fraction of the speed of light. If a supernova occurred within 30 light years of Earth, the radiation would strip away our ozone layer, sterilize the surface, and end most life as we know it. The sky would brighten, the atmosphere would burn, and in a matter of days, billions of years of evolution would be undone. But we're fortunate. The nearest star capable of going supernova is hundreds of light years away, far enough that we can watch without fear, far enough that when it finally explodes, perhaps already has and we simply haven't seen the light yet, we'll witness beauty rather than destruction. The universe keeps its most dangerous toys at a safe distance from us, at least for now. Yet the supernova itself is only the beginning of the story. What's left behind is in many ways even stranger and more dangerous than the explosion itself. When the core of a massive star collapses, if it's not quite heavy enough to form a black hole, it becomes something else. Something small, dense, and spinning with almost unimaginable speed. It becomes a neutron star. Picture this. Take the mass of our entire sun, a sphere over 1 million kilometers in diameter, and compress it down to the size of a city, maybe 20 kilometers across. That's a neutron star. Every cubic centimeter of its surface weighs as much as a mountain. The gravity is so intense that if you could somehow stand on it, which you absolutely could not, you would be instantly flattened into a layer of atoms less than a single molecule thick. There would be no falling, no gradual crushing, just instantaneous conversion from a three-dimensional being into something resembling a very thin coat of paint on an impossibly dense sphere. But neutron stars don't just sit there. Many of them spin, and not slowly. Some rotate hundreds of times per second, their surfaces moving at a substantial fraction of the speed of light. These are called pulsars, and they sweep beams of radiation across space like cosmic lighthouses. If Earth happened to lie in the path of one of these beams, we would be bathed in high-energy particles and electromagnetic radiation strong enough to damage our atmosphere and harm life on the surface. The fastest known pulsar, designated PSRJ 1748-2446 AD, rotates 716 times every single second. 716 complete rotations. Imagine standing on the equator of such an object, though of course you couldn't. The surface would be moving at nearly a quarter of the speed of light. The centrifugal forces alone would be tearing at the star's structure, testing the very limits of what matter can endure. And the magnetic fields. Neutron stars possess magnetic fields trillions of times stronger than Earth's. These fields accelerate particles to tremendous energies, creating jets of radiation that stream out from the star's magnetic poles. If you were anywhere near a pulsar, even millions of kilometers away, the radiation would cook you. Your cells would be torn apart by high-energy photons and charged particles. There would be no defense, no shelter. The very atoms of your body would be ionized and scattered. But here's something to help you sleep easier tonight. The nearest known neutron star is still over 400 light-years away. That's 4 trillion kilometers. The light reaching your eyes right now from that star left its surface before telescopes were invented, before anyone knew that dead stars even existed. One distance, that simple fact of cosmic geometry, is one of our greatest protections. Still, neutron stars are not the most dangerous objects out there. They're not even close. They're simply one category in a vast catalogue of cosmic hazards, each more extreme than the last. As we drift deeper into this inventory of universal dangers, you might find yourself wondering, with so many ways the cosmos can kill, how does anything survive? How did we get here? The answer, which we'll return to again and again tonight, lies in a combination of distance, timing, and extraordinary luck. We live in a quiet neighborhood of the galaxy. We orbit a stable, well-behaved star. We're protected by a magnetic field, an atmosphere, and the vast empty spaces between stars. But this safety is not guaranteed. It never has been. Throughout Earth's history, cosmic dangers have reached us. Asteroids have struck. Radiation from distant supernovae may have triggered ice ages and mass extinctions. The universe is not trying to kill us, but it's not trying to protect us either. It simply is, vast and indifferent, filled with wonders and horrors in equal measure. Let's move on. Because if neutron stars seem extreme, wait until you learn what happens when the collapsing core of a star is just a bit more massive. When gravity wins completely, when nothing, not even light itself, can escape. We're about to encounter something that breaks the rules of space and time, something that was once thought to be purely theoretical, a mathematical curiosity that couldn't possibly exist in the real universe. And yet they're out there, millions of them, scattered throughout every galaxy, objects so dangerous that merely approaching one would seal your fate long before you arrived. But before we get there, take a breath. Let your thoughts settle like dust. The universe is vast and we have all night to explore it. There's no rush, no urgency. Just a slow drift through the darkness, past objects that remind us how fragile and precious our little corner of space truly is. And perhaps, as you begin to relax, you'll find something oddly comforting in these extremes. They're out there, yes, but we're here, safe, warm, protected by distance and fortune. The deadly objects of the universe spin and burn and crush, but tonight, they're just stories. Just ideas to contemplate as sleep begins to pull you gently under. Soon, we'll talk about black holes, about the way they warp space and time, about what happens at the boundary where nothing can return. But for now, rest. Let your mind wander among the pulsars and neutron stars, those impossible spheres of matter spinning in the dark. They've been out there for millions of years, and they'll be there for millions more. The universe takes its time, and so should we. The stars continue their ancient dance. The galaxy turns, and here, on this small world, you're drifting towards sleep, safe from all the dangers that light years and time have placed between us and them. There's more to explore, much more, but it will wait. The deadly objects of the universe are patient. They've been waiting for billions of years. They can wait a bit longer while we rest and prepare for the next part of our journey, deeper into the cosmic dark, where even stranger dangers lurk. Black holes. Even the name sounds ominous, doesn't it? A hole in space itself, a tear in the fabric of reality, where the laws of physics bend and eventually break down completely. For centuries they were thought to be impossible. Even Einstein, whose equations predicted their existence, didn't believe they could actually form. He thought the universe would somehow prevent such extreme objects from coming into being. He was wrong. Black holes are real. They exist throughout the universe, ranging in size from a few times the mass of our sun to monsters billions of times more massive, lurking at the centers of galaxies, and they are, without question, among the most dangerous objects in existence. To understand why black holes are so deadly, we need to understand what they really are. They're not holes in the traditional sense, not empty voids or tunnels to other dimensions. A black hole is a region of space where matter has been compressed so densely that its gravity becomes overwhelming, so strong that it warps space-time itself into a trap from which nothing can escape. Not matter, not light, not even information, according to some interpretations of physics. This point of no return is called the event horizon. It's not a physical surface like the ground beneath your feet or the surface of a star. It's simply a boundary in space, a line that once crossed means you can never come back. Outside the event horizon, you can still escape if you have enough speed and power. Inside it, you're already gone. You could fire the most powerful rocket ever conceived, could somehow convert your entire body mass into pure thrust, and you still couldn't reach the boundary again. The space inside the event horizon is flowing toward the singularity at the center faster than light can travel outward. You're not just trapped, you're already falling, and nothing in the physics we understand can stop it. Now let's talk about what happens if you approach a black hole. Let's say you've somehow acquired a spacecraft capable of traveling to one of the nearest stellar mass black holes, perhaps about 10 times the mass of our sun, maybe a few thousand light years away. As you approach, everything seems fairly normal at first. Space looks like space, stars shine in the distance, but as you get closer, strange things begin to happen. First, you notice that the stars behind the black hole look distorted. The black hole's gravity is so strong that it bends light, acting like a lens. Stars that should be hidden directly behind it become visible, their light bent around the event horizon. You see multiple distorted images of the same stars stretched and warped into arcs and rings. It's beautiful in a way, but also deeply unsettling. You're seeing the geometry of space itself being twisted into shapes that shouldn't exist. As you move closer still, you begin to notice another effect. If you're looking back at the rest of the universe, you see something extraordinary: time dilation. Because of the intense gravity, time near a black hole moves differently than time far away. To you, in your spacecraft, everything feels normal. Your watch ticks at the normal rate, your heart beats at its usual rhythm. But when you look back at the stars, at the galaxy behind you, you see them moving faster. Not much faster at first, but noticeably so. If someone back home were sending you messages, they would arrive faster and faster, their voices sounding increasingly high-pitched and sped up as the time dilation effect increased. But here's the really unsettling part. From their perspective, back in the normal universe, you're slowing down. Your messages to them arrive slower and slower. Your voice deepens and stretches out. As you approach the event horizon, from their point of view, you slow down to a crawl. You never quite seem to reach the horizon. You fade, redshift, and eventually disappear, but you never actually cross, not in their time frame. To them, you're frozen at the edge forever. But in your experience, you absolutely do cross. And once you do, something truly horrific begins to happen. Something so strange that it has its own name: spaghettification. Imagine you're falling feet first toward the black hole. As you cross the event horizon, you might not notice anything dramatic immediately. For a large black hole, supermassive like the ones at the centers of galaxies, the event horizon is so far from the central singularity that the tidal forces at the horizon are actually quite mild. You could cross it alive and aware, though your fate would already be sealed. But as you continue falling inward, the tidal forces grow rapidly stronger. Here's the problem: your feet are closer to the singularity than your head. That means your feet feel a stronger gravitational pull than your head does. With Earth's gravity, this difference is negligible. But near a black hole, it's not negligible. It's enormous. At first, you might feel a gentle stretching sensation, as if someone were pulling on your legs, but this sensation grows and grows. Within seconds or minutes, depending on the size of the black hole, the difference in gravitational force between your feet and your head becomes unbearable. Your body begins to stretch, not metaphorically, actually stretch. The space between your atoms increases, your bones elongate, your tissues pull apart. You're being drawn out like taffy, becoming longer and thinner with every moment. At the same time, you're being compressed from the sides. The tidal forces don't just pull you lengthwise, they squeeze you narrower. You become a thin stream of matter, stretched into something resembling a strand of spaghetti, hence the term. Long before you reach the singularity, you've been torn apart at the molecular level, then the atomic level, then even the subatomic particles that once made up your body are ripped apart and compressed into a one-dimensional thread falling toward the center. And what is that center? The singularity. This is the point where all the matter that ever fell into the black hole has been compressed to infinite density. Our physics breaks down here. We simply don't know what happens at the singularity. General relativity, our best theory of gravity, says that space-time curvature becomes infinite. That means all our equations produce nonsense, infinities, and undefined values. Some physicists think quantum effects, which we don't yet understand, might prevent true singularities from forming. Others think they're real and represent places where the universe simply doesn't make sense anymore. Either way, by the time you reach this point, if the concept of you even has meaning anymore, the journey ends. For smaller black holes, stellar mass ones formed from collapsed stars, the experience would be even worse. The event horizons are much smaller, closer to the singularity, which means the tidal forces at the horizon itself are already intense. You might be torn apart before you even cross the point of no return. Death would come quickly, but not pleasantly. Now here's a disturbing thought. There might be black holes much smaller than stellar mass ones. Theoretical primordial black holes formed in the early universe could be the size of atoms, but with the mass of mountains. If one of these passed through Earth, it would slice through rock and metal like they weren't there, leaving a microscopic tunnel and possibly triggering earthquakes and volcanic eruptions from the sudden displacement of mass. If one passed through your body, you wouldn't feel it, not directly, but the gravitational wake might disrupt your cells on a catastrophic level. These objects, if they exist, could be anywhere, invisible, tiny, and deadly. Fortunately, we've never detected one. And most physicists think primordial black holes, if they exist at all, are extremely rare. But the fact that they're even theoretically possible is a reminder of how strange and dangerous the universe can be. Beyond the immediate danger of being torn apart, black holes pose another threat: radiation. Wait, didn't we just say nothing escapes a black hole? That's true. But just outside the event horizon, in the intense gravitational and magnetic fields that often surround black holes, matter gets heated to extraordinary temperatures. When gas falls toward a black hole, it forms an accretion disk, a swirling maelstrom of superheated material orbiting at a significant fraction of the speed of light. Friction in this disk heats the gas to millions of degrees, causing it to emit intense X-rays and gamma rays. If Earth were orbiting a black hole at a safe distance, say where the tidal forces weren't a problem, we'd still be bathed in lethal radiation from the accretion disk. Our atmosphere would be stripped away, the surface would be sterilized. Any planet near an actively feeding black hole is a dead world. The radiation environment is simply too extreme for any life as we know it to survive. Some black holes also produce jets, narrow beams of particles and radiation that shoot out from their poles at nearly the speed of light. These jets can extend for millions of light years, carving through space and illuminating vast regions of the galaxy. If one of these jets happened to be pointed at Earth, even from thousands of light years away, it could deliver a dose of radiation comparable to a nearby supernova. Mass extinction would follow. And yet, despite all these dangers, black holes play a crucial role in the universe. They help regulate star formation in galaxies. The supermassive black holes at galactic centers, monsters containing millions or billions of solar masses, shape the evolution of entire galaxies through their gravitational influence and the energy they release. In a strange way, these most dangerous objects are also architects, helping to create the structure and order we see in the cosmos. The nearest known black hole to Earth is about 1,500 light-years away. That's close in galactic terms, but still safely distant. It poses no threat to us. The vast majority of black holes are far away, orbiting in binary systems with normal stars, or sitting quiet and dark in the space between stars, invisible and undetectable except through their gravitational effects. But the universe is old, and space is vast, and statistically, over the lifetime of our galaxy, there's a small but non-zero chance that a black hole could wander into our neighborhood. Not tomorrow, not in a million years, but perhaps someday in the distant future, long after humans have either vanished or evolved into something unrecognizable. The odds are tiny, but they're not zero. The universe keeps its dangerous objects on long leashes, but sometimes those leashes bring them close. As you lie there, contemplating the darkness behind your eyelids, think about this. Right now, at this very moment, there are millions of black holes scattered throughout our galaxy. Most are small, the remnants of dead stars. Some are large, the ancient hearts of galaxies long since merged with our own. They sit in the dark, invisible, pulling at the fabric of space, waiting. Not for us, specifically. They don't wait. They don't hunger. They simply exist, consequences of gravity and density, cosmic endpoints where matter and energy go to disappear from the universe. And yet, here we are, nowhere near them, protected by the sheer vastness of space, the simple fact that the universe is mostly empty. Black holes are dangerous, yes, perhaps the most dangerous objects in existence. But they're also rare, and space is large. And for now, and for a very long time to come, we're safe. The black holes spin and feed and warp reality, but not here, not anywhere close to here. We're in a quiet place, a gentle place, where stars shine steadily and gravity behaves predictably, and life can emerge and grow and wonder about the dangers that lie far beyond. Sleep comes easier when you remember that. The universe is dangerous, but it's also distant, and distance, simple empty space, is often all the protection we need. If black holes are the universe's permanent traps, then gamma-ray bursts are its shotgun blasts, brief, violent explosions of energy so intense that they represent the brightest electromagnetic events known to occur in the cosmos. For a few seconds or minutes, a gamma-ray burst can outshine every star in its host galaxy combined, and if one were to occur close enough to Earth, aimed in our direction, it would be a catastrophe of almost unimaginable proportions. The fact that we're still here, that life has persisted on Earth for billions of years, suggests either that we've been extraordinarily lucky, or that these events are rare enough and space vast enough that the odds of a direct hit remain mercifully small. But let's understand what these things are and why they're so dangerous. Gamma-ray bursts, or GRBS, come in two main varieties. Short duration bursts, lasting less than 2 seconds, are thought to result from the collision and merger of neutron stars or a neutron star with a black hole. Long-duration bursts, which can last from a few seconds to several minutes, are associated with the deaths of extremely massive stars, the collapse of a stellar core into a black hole accompanied by a supernova explosion. In both cases, the result is a focused beam of gamma rays, the highest energy form of electromagnetic radiation shot out from the poles of the collapsing or colliding objects. These beams are narrow, perhaps only a few degrees wide, like cosmic searchlights sweeping through space. That's actually fortunate because it means that for every gamma-ray burst we detect, there are many more pointing in other directions that we never see. But it also means that when one is aimed at you, you receive an enormous concentration of energy. How much energy are we talking about? A typical long-duration gamma-ray burst releases as much energy in a few seconds as our sun will produce in its entire 10 billion-year lifetime. That's not a metaphor or an exaggeration. It's the actual measured energy output, and all of that energy is concentrated into a narrow beam. If you happen to lie in the path of that beam, you're exposed to a flood of high-energy photons, gamma rays that can penetrate deep into planetary atmospheres and even into the ground itself. Now, let's imagine, just as a thought experiment, what would happen if a gamma-ray burst occurred relatively nearby, say a few thousand light-years away, and its beam happened to be pointing directly at Earth? First, you should know that this scenario, while theoretically possible, is extremely unlikely. Gamma-ray bursts are rare events, occurring perhaps once per galaxy every few 100,000 to 1,000,000 years. And the odds that one would both occur close to us and be aimed precisely in our direction are very small. But let's explore it anyway, because understanding the danger helps us appreciate our current safety. The gamma rays would arrive without warning, traveling at the speed of light. There would be no advance notice, no time to prepare. One moment, everything is normal. The next, Earth is being bombarded with high-energy radiation. The gamma rays would hit our atmosphere, and this is where things get complicated. The atmosphere would absorb most of the gamma rays, which sounds like good news. We wouldn't be directly irradiated at the surface, but the absorption process itself would cause tremendous damage. When gamma rays collide with molecules in the upper atmosphere, they trigger a cascade of chemical reactions. Oxygen and nitrogen, the primary components of our air, would be broken apart and recombined into nitrogen oxides, the same compounds that create smog and acid rain. But this wouldn't be ordinary smog. This would be a global chemical catastrophe. The nitrogen oxides would rapidly destroy the ozone layer, that thin shield of molecules high in the stratosphere that protects life on Earth from the sun's ultraviolet radiation. Within days or weeks, the ozone layer would be depleted by 50% or more. The sun's ultraviolet rays, no longer filtered, would reach the surface at much higher intensities. DNA damage would increase dramatically. Plants, which are particularly sensitive to UV radiation, would struggle. Phytoplankton in the oceans, the base of the marine food web, and a critical part of Earth's oxygen production, would die off in massive numbers. On land, crops would fail. Animals, including humans, would suffer increased rates of skin cancer and eye damage, but that's just the beginning. The nitrogen oxides in the atmosphere would also contribute to acid rain on a global scale, further stressing ecosystems. The changes in atmospheric chemistry might trigger a cooling effect as the brown haze of nitrogen oxides reflects sunlight back into space. A temporary ice age could follow, adding climate stress on top of radiation damage. The combination of increased UV radiation, disrupted food chains, acid rain, and climate change would likely trigger a mass extinction event, similar in scope to some of the worst extinctions in Earth's history. And the terrifying part, once the gamma rays hit, it would be far too late to do anything about it. By the time we detected the burst, the damage would already be done. We might see a flash of light in the sky as the gamma rays ionize the upper atmosphere, creating a brief, eerie glow. Astronomers might detect the event with space-based telescopes, but within hours, the ozone depletion would begin, and within weeks, the consequences would become apparent. Some scientists have speculated that gamma-ray bursts may have played a role in past mass extinctions on Earth. The Ordovician extinction, about 450 million years ago, is one candidate. It was a time when life was concentrated in the oceans, and a sudden increase in UV radiation would have devastated shallow water ecosystems. We can't prove that a gamma-ray burst caused this extinction. There's no smoking gun, but the pattern of extinction is consistent with an event that would have removed the ozone layer and bathed the planet in harsh radiation. How close would a gamma-ray burst need to be to cause this kind of damage? Estimates vary, but most scientists agree that a burst within about 6,000 to 8,000 light-years, if aimed at us, would be sufficient to trigger serious ozone depletion and ecological disruption. Within our galaxy, the Milky Way, which is about 100,000 light-years across, there are regions with massive stars that could potentially produce such bursts. But again, the requirements are strict. The star must be massive enough, it must collapse in just the right way, and the beam must be pointed precisely at Earth. When you multiply all these probabilities together, the risk is small, though not zero. The good news, if there is good news in this scenario, is that astronomers can identify stars that are candidates for producing gamma-ray bursts. These are extremely massive stars, often Wolf-Rayet stars, with particular characteristics that suggest they're near the end of their lives. By mapping these stars, scientists can assess whether any of them pose a potential threat. So far, there are no known candidates within the danger zone that are both close enough and oriented in a way that would point their eventual gamma-ray burst toward Earth. The nearest serious candidate is much farther away, comfortably outside the range where it could do significant damage. Still, the universe is old, and our sun and solar system have been orbiting through the galaxy for over 4 billion years. During that time, we've passed through different neighborhoods, moved through spiral arms where star formation is higher, and been exposed to various cosmic environments. Statistically, it seems likely that Earth has been in the path of distant gamma-ray bursts before. We may have experienced minor ozone depletion events that we have no record of, or been far enough away that the effects were minimal. The fact that life has persisted suggests that we've either been lucky or that the galaxy is kind enough and empty enough that even these devastating events are spread out in space and time. Gamma-ray bursts also remind us of something important about the universe. It's not static. Stars are born, live, and die. Some die quietly, fading away as white dwarfs. Others die violently, in supernovae or hypernovae, sometimes producing gamma-ray bursts. These events release energy back into the galaxy, enrich the interstellar medium with heavy elements, and shape the conditions for future star formation. In a sense, gamma-ray bursts are part of the cycle of creation and destruction that has been ongoing since the first stars formed billions of years ago. As you relax and let these thoughts drift through your mind, consider the strange balance the universe maintains. It's violent and creative in equal measure. The same supernova that could threaten life also creates the elements necessary for life. The carbon in your body, the oxygen you breathe, the iron in your blood, all of it was forged in the cores of massive stars and scattered into space by supernova and similar events. Without stellar death, there would be no planets, no chemistry complex enough to support life, no us. The universe builds with one hand and destroys with the other, and somehow, in the space between, life finds a way. Gamma-ray bursts are out there, occurring in distant galaxies, flashing across the universe like signals from events we can barely comprehend. We detect them regularly, several times a week, our satellites picking up the brief flashes of gamma rays from billions of light-years away. Each one represents a cataclysm, a star's final moment, a collision between dead suns. Each one is a reminder that the universe operates on scales of energy and violence that dwarf anything we experience on Earth. And yet we sleep soundly, most of us unaware that these things are happening, because they're far away, because space is vast, because the odds are in our favour. The deadly bursts flash through the cosmos, but here, in our quiet corner, the night is peaceful. The stars shine steadily. The galaxy turns. And we're safe, protected by distance and statistics and the simple fact that the universe, for all its dangers, has more empty space than anything else. Let that thought comfort you as you drift. The gamma-ray bursts will continue far away, part of the universe's grand and violent dance, but not here, not tonight. Tonight, we're simply observers, learning about the dangers from a safe distance, appreciating the invisible luck that has kept our world safe for so long, and will likely keep it safe for billions of years to come. Among all the deadly objects in the universe, magnetars occupy a special category of extremes. They are a subclass of neutron star, but with magnetic fields so powerful, so intense, that they exceed anything else in the known cosmos. If neutron stars are already beyond our ability to truly comprehend, magnetars take that incomprehensibility and multiply it 1,000-fold. They are objects where the fundamental forces of nature are stretched to their absolute limits, where physics enters regimes we cannot replicate in any laboratory, where even approaching within 1,000 kilometers would be fatal in ways both immediate and strange. To understand magnetars, we need to first understand magnetic fields themselves. You're familiar with magnets, the small ones that stick to your refrigerator, the ones children play with. Earth itself has a magnetic field, generated by the motion of molten iron in its outer core. This field is strong enough to deflect solar wind and protect us from radiation, strong enough to guide compass needles, but still relatively weak on the cosmic scale. A typical refrigerator magnet is actually stronger than Earth's magnetic field. Now take that concept and scale it upward in ways that break intuition. The Sun has a magnetic field too, stronger than Earth's, and responsible for phenomena like sunspots and solar flares. A typical neutron star has a magnetic field about 1 trillion times stronger than the Sun's. That's already an almost unimaginable jump in intensity. But a magnetar has a magnetic field another 1,000 times stronger than a regular neutron star. We're talking about magnetic fields on the order of 1 billion Tesla, perhaps even more in some cases. To put that in perspective, the strongest continuous magnetic field ever created by humans in a laboratory is around 45 Tesla, and it requires enormous superconducting magnets and vast amounts of energy to maintain. The Earth's magnetic field, by comparison, is about half a 10,000th of a Tesla. A magnetar's field is more than 10 billion times stronger than anything we can produce, and trillions of times stronger than Earth's protective cocoon. This is not just a quantitative difference. At these field strengths, entirely new physical phenomena emerge. What would such a field do? Let's start with something relatively benign, relatively being a very relative term here. A magnetic field this strong would affect atoms themselves. The electron clouds surrounding atomic nuclei would be distorted, stretched into elongated shapes aligned with the field. Chemistry as we know it would cease to function normally. Molecules would behave differently. If you could somehow bring a sample of ordinary matter into a magnetar's field, assuming it wasn't instantly vaporized by other effects we'll discuss, its atomic structure would be rearranged. Elements would have different properties. The periodic table would need to be rewritten. But of course, you'd never get close enough to test this experimentally, because long before you reached the magnetar's surface, other effects would kill you. the magnetic field would interact with your body at the most fundamental level. You see, your body, like all matter, is made of atoms, and atoms contain charged particles, protons and electrons. In a strong magnetic field, charged particles experience forces. In a field as strong as a magnetar's, even from a considerable distance, these forces would be catastrophic. If you somehow found yourself within about 1,000 kilometers of a magnetar, the magnetic field would begin to affect the behavior of ions in your body. Nerve signals, which rely on the movement of sodium and potassium ions, would be disrupted. You might experience strange sensations, hallucinations, or immediate unconsciousness as your nervous system stopped functioning correctly, but that would be the least of your problems. The magnetic field would also induce electrical currents in any conductor, including the salty fluids in your cells. These currents would heat your body from the inside, much like a microwave oven heats food. But again, this would happen so quickly and with such intensity that you wouldn't feel pain, not in any meaningful sense. Your consciousness would be gone before your brain could process the information. Death would be measured in tiny fractions of a second. And if you were closer still, say within 100 kilometers, the magnetic forces would begin to act directly on the atoms themselves. At this range, the field is strong enough to overcome the electromagnetic forces that hold atoms together in molecules. Your body would quite literally be pulled apart at the molecular level, not by tidal forces like near a black hole, but by magnetic forces that discriminate based on the quantum properties of particles. It would be dissociation on a fundamental level, a kind of disintegration that's hard even to describe because we have no analogy for it in everyday experience. But magnetars don't just sit quietly radiating dangerous magnetic fields. They're also incredibly active. Young magnetars, those that formed recently in cosmic terms, perhaps within the last few thousand years, go through periods of intense activity. The magnetic field, which is anchored in the solid crust of the neutron star, can become twisted and stressed as the star's interior and exterior rotate at slightly different rates. Eventually, the stress becomes too great and the crust fractures. When this happens, it's called a starquake. The solid surface of the neutron star, material so dense that a teaspoon would weigh as much as a mountain, cracks and shifts. This sudden rearrangement releases enormous amounts of energy. The magnetic field lines, twisted and compressed, snap and reconnect in violent magnetic reconnection events. The result is a burst of X-rays and gamma rays so intense that it can be detected across the galaxy. These bursts are brief, often lasting less than a second, but their brightness is extraordinary. In December of 2004, a magnetar known as SGR 1806-20, about 50,000 light-years away in our galaxy, experienced a particularly large flare. For a tenth of a second, this object, roughly 20 kilometers across and farther from us than the diameter of the entire Milky Way, was the brightest object in the sky besides the Sun. Its radiation temporarily ionized Earth's upper atmosphere, disrupting radio communications, and this was from 50,000 light-years away. If a magnetar flare like that had occurred closer, say within a few thousand light-years, the effects could have been similar to a gamma-ray burst, potentially damaging our ozone layer and threatening life on Earth. If it occurred within a few hundred light-years, it would be catastrophic. The burst of high-energy radiation would strip our atmosphere, sterilize the surface, and possibly cause permanent damage to the planet's habitability. Fortunately, magnetars are rare. There are only about 30 known magnetars in our galaxy, out of hundreds of millions of stars, and even among those, only a few are young and active enough to produce major flares. The nearest known magnetar is still thousands of light-years away, far enough that its occasional outbursts are merely interesting astronomical events rather than threats. But the fact that they exist at all, that the universe permits objects this extreme, is both fascinating and humbling. Magnetars also challenge our understanding of physics. The conditions in and around these objects are so extreme that they approach the limits where quantum mechanics and general relativity, our two most successful theories of nature, begin to overlap and potentially conflict. Near a magnetar, space-time is warped by the intense gravity of the neutron star, while simultaneously the quantum behavior of particles is affected by the phenomenal magnetic field. Understanding magnetars requires physics that we're still developing, theories that can handle both gravity and electromagnetism in these extreme regimes. Some physicists speculate that magnetars might be laboratories for exotic physics. Perhaps the intense magnetic fields create unusual particles or phenomena that can't exist anywhere else in the universe. Perhaps the conditions inside a magnetar allow us to test theories about how matter behaves at nuclear densities, in environments we can never hope to replicate on Earth. In this sense, magnetars are not just dangers, they're also teachers, offering us glimpses into realms of physics that lie beyond our everyday experience. As you lie there breathing slowly, letting these ideas wash over you like waves, think about the hierarchy of extremes we've explored so far. Neutron stars, already objects of unimaginable density and gravity, black holes, regions where space-time itself breaks down, gamma-ray bursts, explosions that outshine galaxies, and now magnetars, neutron stars on steroids, with magnetic fields so strong they rewrite the rules of matter. Each one is a reminder that the universe is far stranger and more dangerous than our senses and intuition suggest. And yet, each one also reminds us of our cosmic context. We live in a universe where such things exist, but exist far away. Our little corner of space, this solar system orbiting a quiet yellow star, is remarkably safe. No nearby magnetars, no imminent gamma-ray bursts aimed at us, no rogue black holes on a collision course. The universe has arranged itself, through no intention or design, in a way that permits this small island of calm. It's worth noting that the same processes that create these deadly objects also create the conditions for life. The supernovae that form neutron stars, and sometimes magnetars, also scatter heavy elements into space. The energy released by black holes and magnetars can trigger star formation in nearby clouds of gas and dust. The universe's violence and creativity are two sides of the same coin. Without the deaths of massive stars, without the extreme physics of compact objects, the cosmos would be a much simpler and emptier place. There would be no planets, no chemistry, no life, no one to contemplate these mysteries. So, as dangerous as magnetars are, as lethal as their magnetic fields and flares can be, they're also part of the ecosystem of the universe. They play a role, however indirect, in the grand story of matter and energy, structure and chaos that has been unfolding for nearly 14 billion years. They're out there, spinning in the dark, their magnetic fields twisting and snapping, occasionally sending bursts of radiation racing across space. But here, we're safe. We're far from their reach. And tonight, as you drift towards sleep, you can appreciate them as one more wonder in the vast catalogue of cosmic extremes. Dangerous, yes, but also distant, and therefore transformed from threat into spectacle, from nightmare into dream. At the heart of nearly every large galaxy, including our own Milky Way, there sits a supermassive black hole. These are not the stellar remnants we discussed earlier, the black holes formed from collapsing massive stars. These are monsters, containing millions or even billions of times the mass of our Sun, concentrated in regions smaller than our solar system. They're so massive that their gravity shapes the motion of stars across the entire galactic center. And when they feed, when matter falls into their gravitational wells, they become some of the brightest and most energetic objects in the universe. They become quasars and active galactic nuclei, beacons of deadly radiation that can shine across billions of light years. To understand how dangerous these objects are, we need to understand what happens when a supermassive black hole actively feeds on surrounding matter. In the early universe, when galaxies were younger and more chaotic, collisions between galaxies were more common. Gas clouds and stars would be funneled toward the central black hole, providing a feast of material. Even today, in some galaxies, events like the disruption of a star that wanders too close can trigger a temporary period of intense activity. The matter doesn't fall straight into the black hole. Because it has angular momentum, it spirals inward, forming an accretion disk, much like the disks around stellar mass black holes, but on a vastly larger scale. This disk can be light years across, a swirling vortex of gas heated to millions of degrees by friction and gravitational compression. The inner regions of the disk orbit at a significant fraction of the speed of light, and the energy released as matter spirals toward its doom is staggering. A large, actively feeding supermassive black hole can outshine all the stars in its host galaxy combined. Think about that for a moment. A galaxy contains hundreds of billions of stars, each one a nuclear furnace. And yet, the energy released by matter falling into a single supermassive black hole can produce more light than all of those stars put together. This energy isn't just visible light either. It spans the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. And it doesn't radiate uniformly. Much of it is concentrated into narrow jets that shoot out from the poles of the black hole, perpendicular to the accretion disk. These jets are among the most powerful phenomena in the universe. They're streams of particles, mostly electrons and protons, accelerated to nearly the speed of light by the tangled magnetic fields near the black hole. These particles carry enormous amounts of energy, and when they interact with surrounding gas clouds, or even with the intergalactic medium, they create vast glowing lobes that can extend for millions of light years. The energy in these jets is so great that a single active galactic nucleus can affect the evolution of its entire host galaxy, regulating star formation and heating gas across enormous volumes. Now imagine if Earth and our entire solar system were located near the center of a galaxy with an active supermassive black hole. First, we'd be bathed in intense radiation from the accretion disk. X-rays and gamma rays would flood our planet, stripping away the atmosphere and sterilizing the surface. The radiation levels would be thousands or millions of times higher than anything we experience from our sun. No life could survive. No planet could maintain an atmosphere. Even the rocks themselves would be affected, their surfaces altered by the relentless bombardment of high-energy photons and particles. If we were unfortunate enough to lie along the path of one of the jets, the situation would be even worse. The jet's particles, moving at relativistic speeds, would deliver energy densities comparable to a sustained gamma-ray burst. The radiation would not only destroy our atmosphere, it would heat the surface to the point where oceans would boil away and rock would begin to melt. Over time, even the planet itself might be eroded, material blasted away by the unceasing stream of high-energy particles. But here's the crucial point. We're not near the center of our galaxy. We're located about 26,000 light-years from the galactic core, far out in a spiral arm, in a region that's relatively quiet and safe. The supermassive black hole at the center of the Milky Way, known as Sagittarius A star, is currently quiescent. It's not actively feeding, and therefore not producing the dangerous levels of radiation that characterize an active galactic nucleus. If it were active, if it were a quasar, life on Earth would likely never have had a chance to develop. The radiation environment in our galaxy would be too harsh, too unpredictable. And yet, Sagittarius A star hasn't always been quiet. Evidence suggests that in the past, perhaps millions of years ago, it experienced periods of greater activity. During these times, it may have produced jets and intense radiation, though not at the level of a true quasar. These bursts of activity could have had effects on the galactic environment, perhaps even reaching as far as our solar system in the form of increased cosmic ray flux. Some scientists have speculated that past periods of galactic center activity might have influenced Earth's climate or biological evolution, though the evidence is still debated. Looking beyond our own galaxy, quasars represent some of the most distant and ancient objects we can observe. Many of the quasars we detect are billions of light years away, which means we're seeing them as they were billions of years ago, when the universe was much younger. Back then, galaxies were more prone to collisions and mergers, and supermassive black holes had more material to feed on. Quasars were much more common in the early universe than they are today. When we observe a distant quasar, we're seeing light that has traveled for billions of years to reach us. The energy output of these objects is so great that even across such vast distances, they appear as bright points of light in our telescopes. If we could somehow travel to a galaxy hosting an active quasar and position ourselves near, but not too near, the galactic center, we would witness a sky dominated by the blinding glare of the accretion disk. The night sky would never be truly dark. Radiation would rain down continuously. Any planets in such a galaxy, at least those within a certain radius of the center, would be rendered lifeless. This raises an interesting question about the possibility of life elsewhere in the universe. If many galaxies went through quasar phases early in their histories, does that mean life could only emerge later after the quasars faded? Perhaps. Or perhaps life found ways to survive in more distant orbits, in the outer reaches of galaxies where the radiation was less intense. It's possible that the timing of galactic evolution plays a role in determining where and when life can arise. with quasars acting as a cosmic reset button, sterilizing the inner regions of galaxies and forcing life to the periphery. Active galactic nuclei also teach us about the connection between black holes and galaxy evolution. It was once thought that the supermassive black hole at a galaxy's center was just a passive bystander, not really affecting the larger structure. But we now know that's not true. The energy released by an active black hole can drive gas out of the galaxy entirely, shutting down star formation. Conversely, the jets can compress gas clouds in other regions, triggering new waves of star formation. The black hole and the galaxy are intimately connected, each shaping the other's evolution. In this way, the most dangerous objects at the centers of galaxies are also sculptors, artists working on a canvas of gas and stars. They create as much as they destroy, though any life caught in their immediate vicinity would certainly not appreciate the artistry. For us, observing from a safe distance, quasars and active galactic nuclei are reminders of the power that gravity and matter can unleash when combined at the largest scales. As you relax into the feeling of your bed beneath you, the pillow supporting your head, think about the strange fortune of our location. We orbit an average star in an unremarkable spiral arm of a fairly typical galaxy. We're far from the violent core, far from the radiation and chaos that once dominated when our galaxy was young. The supermassive black hole at the center of the Milky Way is dormant now, quietly pulling at the stars around it, but not devouring them in vast quantities, not producing jets or floods of deadly radiation. This quietness is part of why we're here. If Earth had formed closer to the galactic center, or if our galaxy were still in a quasar phase, the story of life might never have been written. The conditions would simply be too harsh. But the universe is old, and galaxies evolve, and by the time our solar system formed about 4.5 billion years ago, the Milky Way had settled into a more peaceful middle age. The quasar days were over, the supermassive black hole was sleeping, and in that calm, life found an opportunity. There's something almost poetic about it. The most powerful engines of destruction in the universe, the supermassive black holes that can outshine entire galaxies, are also, in their dormancy, enablers of life. Their gravity holds galaxies together. Their past activity enriched the intergalactic medium with heavy elements and shaped the distribution of matter. And their current quietness, at least in galaxies like ours, provides a stable environment where stars can form, planets can coalesce, and life can take root. So tonight, as you drift towards sleep, you can rest easy knowing that the quasars, those terrifying beacons of the early universe, are far away in space and time. The supermassive black hole at our galaxy's heart is calm. The deadly radiation that could sterilize worlds is not pointed our way. We're living in a moment of cosmic peace. A window of opportunity carved out by time and distance and the slow evolution of galaxies. It's a fragile peace in some sense because the universe is always in motion, but it's a peace that has lasted for billions of years and will likely last for billions more. The quasars shine in distant galaxies, their light traveling across the void, reaching our telescopes as messages from an ancient and violent past. But here now, we're safe. And that safety, that small bubble of calm in an often chaotic universe, is something worth appreciating as you let go of the day and allow sleep to carry you away. Not all dangers in the universe announce themselves with radiation or gravity wells. Some are silent, invisible, and fast. So fast that by the time you detected one, if you could detect it at all, it would already have passed, leaving destruction in its wake, or perhaps, if we're fortunate, simply sailing past into the darkness beyond. These are the rogue objects of the cosmos, hypervelocity stars flung from galactic centers, rogue planets drifting between the stars, asteroids and comets knocked out of their orbits by gravitational perturbations. They're not exotic in the way black holes or magnetars are. They're made of ordinary matter, governed by ordinary physics. But their potential to cause harm comes not from what they are, but from where they're going and how fast they're moving. Let's start with hypervelocity stars. These are stars that have been accelerated to speeds far greater than the typical orbital velocities of stars in a galaxy. While most stars, including our Sun, orbit the galactic center at a few hundred kilometers per second, hypervelocity stars can reach speeds of 1,000 kilometers per second or more, fast enough to escape the galaxy entirely, their cosmic cannonballs shot out into intergalactic space, never to return. How do stars reach such speeds? The most common mechanism mechanism involves a close encounter with the supermassive black hole at a galaxy's center. Imagine a binary star system, two stars orbiting each other that wanders too close to the central black hole. The tidal forces from the black hole can rip the binary apart. One star gets captured, spiraling toward the black hole, while the other is flung outward at tremendous speed, like a stone from a slingshot. The captured star's gravitational energy is converted into kinetic energy for the ejected star, which goes hurtling out of the galactic core. These stars have been detected, fleeing our galaxy at breakneck speeds. They're rare, but they exist, proof that the universe can create natural projectiles on scales that dwarf anything we can imagine. Now, what would happen if one of these hypervelocity stars happened to pass through our region of space? The odds are extraordinarily low. Space is vast, and even a star moving at 1,000 kilometers per second would take millions of years to cross the galaxy. The chances that its path would intersect with our solar system are minuscule, but if it did happen, the consequences would be severe. A star passing within a light year or so of our solar system would gravitationally disrupt the Oort cloud, a vast shell of icy comets that surrounds the Sun, at a distance of up to a light year or more. This disruption could send a shower of comets into the inner solar system, increasing the risk of impacts on Earth and the other planets for thousands or even millions of years afterward. If the hypervelocity star passed even closer within the Kuiper belt or the orbit of Neptune, the effects would be more immediate and dramatic. The orbits of the outer planets could be perturbed, potentially destabilizing the entire solar system over long timescales. In an extreme case, if a star passed within the orbit of Jupiter or closer, it could eject planets entirely, send Earth and its siblings hurtling into interstellar space, or cast them into the Sun. The solar system as we know it would cease to exist. But remember, this is a scenario with extremely low probability. The galaxy is large, stars are spread out, and even the fastest rogue stars are still just tiny points of light moving through an ocean of emptiness. The real danger from hypervelocity stars is not to us specifically, but to any civilizations that might happen to be in their path, somewhere else the galaxy, at some other time. Now, let's turn to something potentially more concerning: rogue planets. These are planets that have been ejected from their original solar systems and now drift through interstellar space, untethered to any star. They're invisible, emitting no light of their own, and detectable only if they happen to pass in front of a distant star and block its light, or if they pass close enough to a star that their gravity causes a detectable perturbation. How many rogue planets are out there? We don't know exactly, but simulations of planetary system formation suggest there could be billions of them in our galaxy alone, perhaps even outnumbering the stars. During the chaotic early phases of solar system formation, when planets are migrating and their orbits are not yet stable, gravitational interactions can fling smaller planets out into interstellar space. In our own solar system, there's evidence that such ejections may have occurred in the distant past, possibly explaining some features of the outer solar system's architecture. A rogue planet passing through our solar system would be a quieter disaster than a hypervelocity star, but a disaster nonetheless. Depending on its mass and trajectory, it could disrupt planetary orbits, particularly those of the outer planets. If a rogue planet, say roughly Earth-sized or larger, passed through the inner solar system, it could gravitationally scatter the inner planets, including Earth. In a worst-case scenario, Earth could be ejected from the solar system entirely, sent tumbling into the cold darkness of interstellar space. What would that be like? Without the sun's heat, Earth's surface would cool rapidly. Within days, the temperature would plummet below freezing. Within weeks, the oceans would begin to freeze over. Within months, the atmosphere itself would start to condense and fall as snow, primarily nitrogen and oxygen ice accumulating on the frozen surface. Any life on the surface would perish almost immediately, but deep underground, or in the deep oceans near geothermal vents, life might persist for a while longer, sustained by Earth's internal heat rather than the sun's energy. Eventually, though, even that would fade, and Earth would become a frozen, lifeless ball drifting through the dark. Fortunately, the probability of a rogue planet passing through our solar system on a trajectory that would disrupt Earth's orbit is very, very low. Space is incredibly empty. Even though there may be billions of rogue planets in the galaxy itself is so vast that the average distance between them is enormous. The chances of one passing close enough to us to cause harm in the next few million or even billion years are minimal, but non-zero. It's one of those cosmic risks that's always there in the background, too small to worry about on human timescales, but real enough that over the lifetime of the galaxy, such encounters have probably happened to countless worlds. Then there are smaller objects, rogue asteroids and comets, either ejected from other solar systems or simply wandering through interstellar space. These pose a different kind of threat, one that's actually more immediate and measurable. We know that asteroids and comets have struck Earth in the past, and we know that large impacts can cause mass extinctions. The asteroid that ended the reign of the dinosaurs 66 million years ago was about 10 kilometers across. Its impact released energy equivalent to billions of nuclear bombs, triggering wildfires, tsunamis, and a nuclear winter effect that darkened the skies for years. An interstellar object, something not bound to our sun but passing through on a hyperbolic trajectory, would be moving much faster than typical asteroids and comets in our solar system. The higher speed means higher impact energy and therefore more damage for a given size. In 2017, we detected the first known interstellar object passing through our solar system, Oumuamua. It was small, perhaps a few hundred meters in length, and it posed no threat, passing well away from Earth. But its discovery confirmed that interstellar objects do occasionally wander into our neighborhood. If a larger interstellar object, say a few kilometers across, were on a collision course with Earth, we would have very little time to respond. Because it's coming from outside the solar system, we wouldn't have years or decades of warning like we might with an asteroid already in orbit around the Sun. We might have months or even weeks depending on when we detected it. At that point, deflection would be extremely difficult. The object's high speed and the short time frame would make it nearly impossible to mount an effective defense with current technology. Is this likely to happen? Again, the odds are low. Interstellar space is vast, and the chances of a large interstellar object intersecting Earth's orbit are small, but the consequences would be so severe that even a small probability is worth considering. This is why astronomers survey the sky, cataloguing asteroids and comets, looking for anything that might pose a threat. It's also why there's increasing interest in developing planetary defense technologies, systems that could detect and deflect dangerous objects before they reach us. There's a strange irony in all of this. The universe is filled with objects capable of ending life on Earth, not through exotic physics or extreme radiation, but through simple, brute force impact. A big enough rock, moving fast enough, can reset the evolutionary clock, wipe out species, and reshape the planet's surface. And yet, the very emptiness of space, the vast distances between objects, is what has protected us so far. We've been hit before, many times over Earth's history, but the gaps between major impacts are long enough that life recovers, diversifies, and continues. As you lie there, feeling the weight of your body against the bed, the softness of the blanket, think about the fact that right now, at this moment, countless objects are moving through space. Some are bound to stars, following predictable orbits. Others are rogue, drifting between the stars, going wherever gravity and inertia take them. Most will never come near us. They'll pass through empty regions, unseen and undetected, their journeys measured in millions of years. But a few, over the vast stretches of time, will cross paths with planets. Some of those planets will be lifeless rocks. Others, perhaps, will be homes to life, civilizations, beings looking up at their own skies, wondering about the dangers that lurk in the dark. We can't predict every rogue object. We can't map every hypervelocity star or track every rogue planet. The universe is too large, and our instruments, however advanced, can only see so much, but we can appreciate the balance of probabilities, the way the cosmos arranges itself such that danger is real but distant, possible but not imminent. We live in a shooting gallery, but one where the targets are few and far between, and the bullets take millions of years to arrive. Tonight, none of these objects threaten us. No rogue planet is hurtling toward the solar system. No hypervelocity star is bearing down on our neighborhood. No interstellar asteroid is on a collision course with Earth. The sky above is peaceful, the stars following their ancient paths, and we're safe in the quiet spaces between the dangers. Tomorrow, the same will be true, and the day after, and for countless days to come. The universe moves slowly, and so do its threats. And in that slowness, there's time. Time to watch. Time to prepare. Time to sleep soundly, knowing that the odds, for now, are in our favor. We tend to think of space as empty, a vacuum where nothing exists. And in a sense, that's true. The density of matter between stars is incredibly low, far lower than the best vacuum we can create in laboratories on Earth. But space is not truly empty. It's filled with radiation, charged particles, fields and forces, all of which can be deadly in their own subtle ways. Among the most insidious of these invisible dangers are cosmic rays, high-energy particles that constantly rain down on us from all directions, penetrating planets, ships, and even our own bodies. On Earth, we're shielded by our atmosphere and magnetic field, but venture beyond that protection, and cosmic rays become one of the most serious threats to life. Cosmic rays are not rays at all, despite the name. They're particles, mostly protons, but also heavier atomic nuclei, electrons, and even traces of antimatter. They travel through space at a significant fraction of the speed of light, and some of them carry truly enormous amounts of energy. The origin of cosmic rays varies. Some are produced by the sun, especially during solar flares. Others come from supernova remnants, where the shock waves from the exploding star accelerate particles to high speeds. The most energetic cosmic rays, whose origins are still debated, may come from distant galaxies, perhaps accelerated by the jets of active galactic nuclei or other extreme events. When a cosmic ray particle strikes an atom in Earth's atmosphere, it creates a cascade of secondary particles, a shower that spreads out and eventually reaches the surface. These secondary particles are mostly harmless, their energy diffused by the many collisions in the atmosphere, but the primary cosmic rays, before they hit the atmosphere, carry enough energy to damage DNA, disrupt cellular processes, and increase cancer risk. Astronauts in space, beyond the protective blanket of our atmosphere, are exposed to much higher levels of cosmic ray radiation than people on the ground. For short trips, like missions to the International Space Station, which orbits within Earth's magnetic field, the radiation risk is manageable, though still higher than on the surface. But for longer missions, such as a journey to Mars, cosmic ray exposure becomes a serious concern. Astronauts would spend months or years in deep space, far from Earth's magnetic protection, constantly bombarded by high-energy particles. The radiation would increase their lifetime cancer risk significantly. It might also cause damage to the nervous system, leading to cognitive impairment, and could affect the cardiovascular system. Current spacecraft offer little protection against cosmic rays. The particles are so energetic that they pass right through metal hulls and human tissue with ease. Shielding against them would require thick layers of material, adding weight and complexity to the spacecraft. Some proposed solutions include using water or polyethylene, which are more effective at stopping high-energy particles than metal, but even these have limits. The most energetic cosmic rays would penetrate any reasonable amount of shielding. This is one reason why long-duration space travel, and especially interstellar travel, remains so challenging. It's not just about propulsion or life support, it's also about protecting fragile biological organisms from the radiation environment of deep space. On Earth, evolution has shaped life to tolerate a certain background level of radiation, mostly from natural radioactive elements in rocks and from cosmic rays that make it through the atmosphere. But the radiation levels in space are much higher, and life as we know it is not adapted to handle them. Now let's consider what would happen if Earth's protective magnetic field disappeared. This is not just a hypothetical scenario. Earth's magnetic field has weakened in the past, and it occasionally flips, with the north and south magnetic poles swapping positions. During a flip, which takes place over thousands of years, the field weakens significantly, and there may be periods when it's almost gone. During these times, Earth's surface would be exposed to much higher levels of cosmic rays and solar radiation. The immediate effect would be an increase in radiation at the surface, particularly at higher altitudes and latitudes. The ozone layer would be attacked by the increased radiation, breaking down more quickly than it could be replenished. With a weakened ozone layer, more ultraviolet radiation from the sun would reach the surface, increasing DNA damage in living organisms and affecting ecosystems globally. Species sensitive to UV, including phytoplankton, which form the base of the ocean food web, could suffer population declines, rippling through the entire biosphere. Would this cause a mass extinction? Probably not, at least not directly. Life has survived magnetic field reversals in the past, but it would certainly add stress to ecosystems and could contribute to broader environmental changes. Some scientists have speculated that magnetic field reversals might be linked to climate changes or extinction events, though the evidence is still debated. Beyond cosmic rays from natural astrophysical sources, there's another category of high-energy radiation to consider: radiation from human-made or extraterrestrial technologies. If an advanced civilization existed elsewhere in the galaxy, and if they were using technologies that involved high-energy physics, for example particle accelerators on a massive scale, or if they were harnessing the energy of stars, they might inadvertently or deliberately produce beams of radiation that could affect other star systems. This is purely speculative, of course, but it's worth noting that the same technologies that might enable an advanced civilization to travel between stars or manipulate enormous amounts of energy could also, if misused, become weapons or hazards. There's also the concept of a relativistic kill vehicle, a projectile accelerated to a significant fraction of the speed of light. At such speeds, even a small object carries tremendous kinetic energy. If it struck a planet, the impact would release energy equivalent to a large asteroid strike, or worse, depending on the mass and velocity. The object itself wouldn't need to be made of anything exotic. Simple matter, moving fast enough, becomes a devastating weapon. Fortunately, there's no evidence that such things exist or are being used, but the physics is straightforward, and it's something that future spacefaring civilizations, including our own, would need to consider. Closer to home, we have to consider solar radiation, which is a constant presence. The sun emits a stream of charged particles called the solar wind, as well as electromagnetic radiation across all wavelengths. Most of the time, this radiation is steady and predictable, and Earth's magnetic field deflects the charged particles, funneling them toward the poles where they create the auroras. But occasionally, the sun has outbursts, solar flares and coronal mass ejections, where huge amounts of plasma and magnetic field are hurled into space. If a large coronal mass ejection were directed at Earth, it could cause geomagnetic storms that disrupt power grids, satellite communications, and navigation systems. In the modern world, so dependent on technology, this could be a significant problem. The particles from a solar storm can induce currents in power lines, potentially overloading transformers and causing widespread blackouts. In 1859, a massive solar storm known as the Carrington Event caused telegraph systems to fail and even set some equipment on fire. If a similar event occurred today, the damage could be much more extensive, affecting everything from GPS to the internet. For astronauts or satellites in space, solar storms pose a direct radiation hazard. The energetic particles from a coronal mass ejection can deliver doses of radiation high enough to cause radiation sickness or even be lethal, depending on the intensity and duration of the exposure. This is why space weather monitoring is so important. We need to predict solar storms and provide warnings so that astronauts can take shelter and satellite operators can take protective measures. All of this invisible radiation, cosmic rays, solar wind, the remnants of distant supernovae, creates a kind of background hum in the universe, a constant flux of energy and particles moving through space. Most of it passes through us unnoticed. A few cosmic ray particles are hitting your body right now, even as you lie in bed. They pass through the roof, through the walls, through you, leaving barely a trace. Your cells repair the minor damage, and life goes on. But in space, without the atmosphere and magnetic field to shield us, that same radiation becomes a serious hazard. This is one of the great challenges of becoming a spacefaring species. We evolved on a planet with natural protection, and leaving that protection means exposing ourselves to an environment that's fundamentally hostile to life. It's not impossible to overcome. We can build spacecraft with better shielding, develop medical countermeasures to repair radiation damage, perhaps even genetically engineer organisms to be more resistant to radiation. But it's a reminder that space, for all its beauty and mystery, is not a welcoming place. It's a harsh environment where survival requires constant vigilance and advanced technology. As you breathe slowly and let your body relax, think about the fact that right now you're safe. The atmosphere above you is thick enough to absorb almost all the harmful radiation from space. The magnetic field around Earth is deflecting charged particles. The sun is in a relatively quiet phase. All these factors combine to create a bubble of safety, a small zone where life can flourish without constantly battling radiation. This bubble is rare in the universe. Most of space doesn't have it, and that makes Earth and planets like Earth precious. The invisible dangers of space, the cosmic rays and solar storms, the background radiation and high-energy particles, they're always there. but they're manageable as long as we respect them and take precautions. And for now, as you drift towards sleep, they're distant concerns, abstract concepts, not immediate threats. The roof over your head, the atmosphere above that, and the magnetic field above that, they all stand between you and the radiation of the cosmos. You're layered in protection, nested within shields that have been here for billions of years and will be here for billions more. The cosmic rays streak past, mostly unnoticed, and you rest easy, safe in the knowledge that tonight, as every night, the universe's invisible barrage is being quietly, constantly deflected away. We've talked about objects, stars and black holes, particles and radiation, but there's another danger that's so fundamental, so basic, that we often overlook it. The vacuum of space itself, the simple absence of air. It's not dramatic like a supernova or exotic like a magnetar, but it's absolute. In the vacuum of space, there's nothing to breathe, no pressure to hold your body together in the way it's accustomed, no medium to carry away heat or sound. If you were exposed to the vacuum without protection, you would die, though perhaps not in the ways Hollywood often depicts. Let's walk through what would actually happen, slowly and carefully, because understanding the reality of the vacuum helps us appreciate just how finely tuned our existence on Earth truly is. Imagine, for a moment, that you're in a spacecraft and there's a sudden breach. The airlock fails, or a micrometeorite punctures the hull. Suddenly, you're exposed to space. What happens in the first second? First, the air rushes out of your lungs. If you tried to hold your breath, the pressure difference would be too great. The air in your lungs is at roughly 1 atmosphere of pressure, while outside is essentially 0. That pressure differential would force the air out, and if you stubbornly kept your mouth and nose closed, your lungs could rupture. So the first rule, if you somehow find yourself in this situation, is to exhale, let the air go. Next, the moisture on your tongue, in your mouth, and on the surface of your eyes begins to boil, not because the temperature has increased, but because in a vacuum, water boils at any temperature. The liquid water vaporizes rapidly, and you'd feel an intense sensation of dryness. Your eyes, if you kept them open, would be particularly affected, the tears boiling away, though closing your eyes wouldn't help much. You would not explode. Your skin is strong enough to contain your body against the pressure difference. You would swell somewhat as the gases dissolved in your bodily fluids begin to come out of solution, forming bubbles, a condition similar to the bends that divers experience. But you'd remain intact, at least initially. Contrary to popular belief, you would not freeze instantly. Space is cold, in the sense that there's very little matter, and that matter has a very low temperature. But heat transfer in a vacuum is slow because there's no air to conduct heat away from your body. You lose heat only through radiation, which is a much slower process. It would take many minutes for your body to cool significantly. So freezing is not an immediate concern. What would kill you, and fairly quickly, is the lack of oxygen. Your blood, as it circulates through your lungs, would stop picking up oxygen. Within about 15 seconds, the oxygen already in your blood would be depleted by your brain and other organs. You'd lose consciousness. Brain damage would begin within a couple of minutes. Without rescue and repressurization, death would follow in less than 2 minutes. It's a quiet, inexorable process. There's no explosion, no dramatic disintegration, just a rapid, silent shutdown of the biological systems that require air. In a way, it's a reminder that we're not built for space. We're built for the bottom of an ocean of air, a thick atmosphere that presses down on us with the weight of all the gas above. Our bodies expect that pressure, need it, are shaped by it. Take it away, and we simply stop working. But let's broaden the perspective. It's not just humans who can't survive in vacuum. No known form of life can live exposed to space for extended periods. There are some extremophiles, bacteria, and other microorganisms that can survive in vacuum for short times, essentially going dormant until conditions improve. Tardigrades, those microscopic creatures sometimes called water bears, can enter a cryptobiotic state where they shut down almost all metabolic activity and survive extreme conditions, including vacuum. But even they can't thrive there. They're just very good at waiting for better circumstances. The vacuum of space is one of the few truly universal hazards in the universe. It doesn't matter how advanced your biology or technology is. If you're a living organism that relies on chemical processes, you need some kind of environment. You need molecules to interact, reactions to take place, energy to flow. In a vacuum, none of that happens naturally. You need to bring your environment with you. In a suit or a ship, a bubble of pressure and air that mimics the conditions of a planetary surface. This is why spaceflight is so challenging. Every mission requires creating and maintaining a tiny artificial environment, a fragment of Earth carried into the void. Life support systems must provide air, remove carbon dioxide, manage humidity and temperature, all while ensuring that the pressure is maintained. Any failure, any leak or malfunction, and the vacuum begins to intrude. Astronauts live in a constant state of managed risk, aware that only a thin metal shell and a few layers of fabric stand between them and an environment that would kill them in seconds. There's also the question of long-term exposure to low pressure, even if it's not a complete vacuum. On Mars, for example, the atmospheric pressure is less than 1% of Earth's. It's not a total vacuum, but it might as well be for most biological purposes. You can't breathe Martian air, not because it's the wrong composition, though it's mostly carbon dioxide, but because there's so little of it. Even if it were pure oxygen, there wouldn't be enough pressure to get adequate amounts into your bloodstream. You'd suffocate just as surely as in vacuum. Any human presence on Mars will require habitats with pressurized atmospheres, and anyone venturing outside will need spacesuits. The same would be true for the Moon, for asteroids, for anywhere in the solar system except Earth, and perhaps some of the clouds of Venus, though the surface of Venus has its own deadly problems. The vacuum, or near vacuum, is the default state of the universe. Thick, breathable atmospheres are rare exceptions, and yet, despite this, life emerged. On Earth, evolution found ways to extract energy from sunlight and chemical reactions, to build complex structures, to create organisms that could move, sense, think. All of this happened at the bottom of an atmosphere, in the narrow range of pressures and temperatures where liquid water exists and chemical reactions can proceed at useful rates. We are, in a very real sense, creatures of the interface between rock and air, confined to the thin shell of Earth's surface where conditions are just right. Stepping beyond that shell, even a little, brings us into contact with the vacuum and reminds us how fragile our hold on existence is. Every astronaut who has ventured into space has crossed that boundary, left the natural environment of our species, and relied entirely on technology to stay alive. It's a profound experience by all accounts to see the Earth from space, to recognize the thinness of the atmosphere, the darkness of the void, the isolation of our small world. This is another answer to the question we started with. If the universe is so dangerous, how did life appear? Part of the answer is that life didn't appear in the universe at large. It appeared on the surface of a planet, in a place where the vacuum was kept at bay by a thick atmosphere, where water could remain liquid, and where energy from a star could drive the chemistry of life. The universe's dangers, the vacuum, the radiation, the cold, are held back by Earth's environment, and as long as we remain on Earth, or create similar environments elsewhere, we're protected. As you settle deeper into your bed, feel the air around you, the gentle pressure on your skin, the way your lungs fill easily with each breath. It's something we take for granted, this ocean of air, but it's precious. It's the barrier between life and the void, and it's been here, more or less, for billions of years, renewed by volcanic outgassing, by photosynthesis, by the complex interactions between life and planet. The vacuum of space is patient. It surrounds our world, extends in all directions, fills the gaps between stars and galaxies. It's the default state of the cosmos. But here, on this small rock, we've managed to carve out an exception, a bubble of warmth and air and life. And as long as that bubble holds, as long as the atmosphere stays thick and the magnetic field stays strong, we can sleep soundly, knowing that the vacuum is out there, yes, but not in here, not where we are. Tonight, there's no breach, no sudden decompression, no exposure to the void. There's just the comfort of air, the familiar pressure, the easy rise and fall of your chest as you breathe. The vacuum waits, as it always has, but it waits far away. And in this moment, that distance is all that matters. We've explored many of the deadly objects and forces in the universe, things made of matter and energy, phenomena we can observe, measure, and at least partially understand. But now we turn to something stranger, something that makes up most of the universe and yet remains almost entirely mysterious: dark matter and dark energy. These are not objects in the traditional sense. You can't point a telescope at a clump of dark matter and take a picture. You can't feel dark energy pushing against you. They reveal themselves only through their gravitational effects, the way they shape galaxies, bend light, and drive the expansion of the universe itself. And while they're not dangerous in the immediate, visceral way that a black hole or gamma ray burst is, they represent a profound unknown, a reminder that most of the universe is invisible to us, and that we're only beginning to understand the rules by which everything operates. Let's start with dark matter. In the early 20th century, as astronomers studied the motion of galaxies and clusters of galaxies, they noticed something odd. The galaxies were moving too fast. Based on the visible matter, the stars and gas we could see, there wasn't enough gravity to hold the clusters together. The galaxies should have flown apart long ago, but they hadn't. Something invisible, something that didn't emit or absorb light, was providing additional gravitational pull. This invisible something is what we now call dark matter. It doesn't interact with electromagnetic radiation, which means it doesn't shine, reflect, absorb, or emit light. It interacts with ordinary matter only through gravity, and there's a lot of it. Current estimates suggest that dark matter makes up about 27% of the universe's total mass energy, compared to about 5% for ordinary matter, the stuff that makes up stars, planets, and us. What is dark matter made of? We don't know. It's not any of the particles in the standard model of particle physics. It's something else, perhaps a new type of particle that we've never detected directly. Many experiments are underway, trying to catch dark matter particles as they pass through detectors on Earth, but so far we've only seen dark matter's gravitational effects, never the particles themselves. From a certain perspective, dark matter is everywhere. It's passing through you right now, billions of particles every second, moving through Earth and your body without interacting, like ghosts. This sounds unsettling, but it's actually harmless. Because dark matter interacts so weakly with ordinary matter, it has no effect on biological processes. It doesn't ionize atoms, doesn't break chemical bonds, doesn't deposit energy. It's present, but inert, at least as far as we can tell. However, dark matter does shape the universe on large scales. It provides the gravitational scaffolding that allows galaxies to form. In the early universe, dark matter clumped together first, creating gravitational wells into which ordinary matter fell, eventually forming stars and galaxies. Without dark matter, the universe would look very different. Perhaps galaxies wouldn't have formed at all, or would be much smaller and more diffuse. In that sense, dark matter is essential for our existence. It's not a threat. It's a foundation, but there's always the possibility, however remote, that our understanding is incomplete. What if dark matter can interact with ordinary matter under certain conditions? What if there are forms of dark matter that are more active, more dangerous? These are speculative questions not based on any current evidence, but they highlight the uncertainty. We're dealing with something that makes up most of the matter in the universe, and we barely know what it is. That's humbling. Now let's turn to dark energy, which is even stranger. In the late 1990s, astronomers studying distant supernovae made a shocking discovery. The expansion of the universe, which had been slowing down due to gravity, was actually accelerating. Something was pushing space apart, causing galaxies to move away from each other faster and faster. This something is dark energy. Dark energy makes up about 68% of the universe's total mass energy. That means the universe is mostly dark energy, with dark matter second and ordinary matter a distant third, and we have almost no idea what dark energy is. The leading hypothesis is that it's a property of space itself, a kind of intrinsic energy that exists everywhere, even in empty space. Einstein's equations allow for such a thing, called the cosmological constant, but whether that's what dark energy really is remains an open question. What does dark energy do? It drives the expansion of the universe, and as space expands, more space is created, which means more dark energy, which drives even faster expansion. This is a runaway process, and it has profound implications for the future of the cosmos. As dark energy continues to dominate, galaxies that are not gravitationally bound to our local group will be pushed farther and farther away, eventually receding faster than the speed of light. Not because they're moving through space that fast, but because space itself is expanding. They'll disappear beyond the horizon, their light redshifted into invisibility. The universe will become a lonelier place, with fewer and fewer galaxies visible from any given point. In the very distant future, trillions of years from now, if dark energy continues to behave as it does now, the universe could end in a state called the Big Freeze or heat death. all the stars will burn out, all the black holes will evaporate through Hawking radiation, and space will be filled with nothing but a thin, cold soup of particles and radiation, drifting apart forever. It's a quiet, cold, and lonely end, not violent, but final. There's also a more speculative scenario called the Big Rip, which would occur if dark energy grows stronger over time. In this case, the accelerating expansion would eventually overcome all forces, even the ones holding atoms together. First, galaxy clusters would be torn apart, then galaxies, then solar systems, then planets, then molecules and atoms, and finally, even subatomic particles. The universe would be shredded into its most fundamental components, space expanding so fast that nothing could remain intact. This is a more dramatic ending, but it's purely theoretical and not supported by current observations, which suggest dark energy is constant or nearly so. Should we be worried about dark energy? Not in any immediate sense. The effects of dark energy are only noticeable on cosmic scales and time scales. Over the span of a human life, or even the lifetime of the Sun, dark energy's influence is negligible. It's not going to tear apart the solar system tomorrow, or in a billion years, but it does mean that the universe has a fate, an ultimate destination, and that destination is not a return to a big crunch or a cycle of rebirths. It's a slow, cold, endless expansion, 95% of the universe. That means everything we can see, touch, and measure, all the stars and planets, all the atoms in your body, all the light from all the galaxies, represents only 5% of reality. The rest is hidden, interacting with us only through gravity, shaping the cosmos in ways we're only beginning to understand. This is one of the great mysteries of modern science, and also one of its great humilities. We've learned an enormous amount about the universe, but we've also learned how much we don't know. In a way, dark matter and dark energy are not dangers in the traditional sense. They're not going to kill you. They're not threats you can avoid or defend against, but they represent an existential unknown. A reminder that the universe is far stranger than it appears, and that the things we can see are just a small fraction of what's out there. They're the universe's way of telling us that we've only scratched the surface, that there are depths we've yet to explore, questions we've yet to answer. As you lie in the darkness of your room, think about the fact that most of the universe is dark in a very literal sense. Not just an absence of light, but a presence of something unknown, something that fills space and affects everything, but remains invisible. It's as if the universe is mostly a mystery, and the parts we understand, the stars and galaxies and atoms, are just islands of clarity in an ocean of the unknown, and yet we're here, made of that 5%, living on one of those islands trying to make sense of it all. There's something almost comforting about that in a way. It means there's more to discover, more to learn. The universe has not given up all its secrets, and as long as there are mysteries, there's a sense of wonder, a reason to keep looking, keep questioning. Dark matter and dark energy are not enemies. They're puzzles, and solving them will take time, ingenuity, and perhaps a complete rethinking of our understanding of physics. But that's part of the journey. For now, rest easy, knowing that the invisible parts of the universe, the dark matter streaming through your body, the dark energy stretching space, are not here to harm you. They're simply part of the fabric of reality, woven into the cosmos at the deepest levels. They shape galaxies, drive expansion, and remind us that we live in a universe far richer and more complex than our ancestors could have imagined. The darkness is not a threat, it's an invitation to explore. We've traveled far tonight, past neutron stars and black holes, through gamma-ray bursts and magnetar flares, alongside rogue planets and cosmic rays, into the vacuum of space and the mysterious realms of dark matter and dark energy. We've catalogued the deadly objects of the universe, the things that can kill, destroy, and obliterate on scales both intimate and cosmic. And through it all, one question has lingered, the question we started with. If the universe is so dangerous, how did life appear? What protects us? The answer, as you've probably gathered, is not simple. It's not a single shield or a piece of luck. It's a combination of factors, a confluence of circumstances that have, so far, kept Earth and its inhabitants safe from the worst the cosmos has to offer. Let's take a moment to appreciate these protections, these invisible walls between us and the void. First, there's distance. The universe is vast, almost incomprehensibly so. The space between stars is measured in light years, and the space between galaxies in millions or billions of light years. This vastness means that dangerous events, even though they occur regularly on cosmic scales, are spread out. A supernova that happens in a distant galaxy is a spectacle, not a threat. A gamma ray burst from billions of light years away is a data point for astronomers, not a disaster. Distance dilutes danger, turns lethal radiation into faint whispers, and gives us the luxury of observing the universe's violence from a safe remove. Second, there's timing. The universe is old, nearly 14 billion years, and Earth is about 4.5 billion years old. In that time, many dangerous events have happened, but they've been spaced out in time as well as space. The nearest supernova to Earth in recorded history was in 1604, and it was far enough away to be harmless, just a bright new star in the sky. The last major asteroid impact that caused a mass extinction was 66 million years ago, long enough that life recovered and diversified. The universe operates on timescales that are long compared to human lifetimes, even long compared to the lifetime of species. This gives life time to recover from disasters, time to adapt, time to persist. Third, there's Earth's own protection. Our atmosphere absorbs and scatters harmful radiation, protects us from small meteorites, and provides the air we breathe. Our magnetic field deflects the solar wind and cosmic rays, creating a protective bubble around the planet. Even the moon plays a role, stabilizing Earth's axial tilt and contributing to tides, which may have been important for the development of early life. Earth is not just a random rock in space, it's a carefully balanced system that has maintained conditions favourable for life for billions of years. Fourth, there's our location in the galaxy. We're not at the galactic centre, where radiation levels are high and supermassive black holes lurk. We're not in a densely packed region where star collisions or close encounters might be common. We're in a quiet suburban region of the Milky Way, far from most of the action. Our Sun is a stable, middle-aged star, not prone to violent flares or dramatic changes. We orbit at the right distance for liquid water in the so-called habitable zone. All of these factors combine to make our location unusually safe. But even with all these protections, Earth has not been completely safe. Life has faced extinction events, some caused by asteroids, some by volcanic eruptions, some possibly by cosmic rays from nearby supernovae. Each time, life has been pushed to the brink, but each time, it has recovered. The biosphere is resilient, adaptable, capable of bouncing back from disasters that would seem apocalyptic. This resilience is itself a kind of protection, not against the dangers themselves, but against their ultimate consequences. And yet, we have to acknowledge the role of luck. There's no guarantee that a planet will be safe. There's no law of the universe that says life will be protected. We've been fortunate in our location, in our timing, in the stability of our star and planet. But this fortune is not infinite. Over long enough timescales, dangers will arise. Perhaps a nearby star will go supernova. Perhaps a rogue black hole will wander too close. Perhaps an interstellar object will strike Earth. These are low-probability events, but given enough time, low-probability events become certainties. This is why, in the long term, humanity's survival may depend on becoming a multi-planet species, spreading beyond Earth to other worlds, building habitats in space, and ensuring that no single disaster can wipe us out completely. It's a grand vision, and one that's still mostly theoretical, but it's rooted in the recognition that Earth, for all its protections, is not invulnerable. The universe is dangerous, and relying on a single planet, no matter how well protected, is a risk. But tonight, as you lie here, those long-term concerns can wait. Tonight, we're safe. The nearest black hole is thousands of light years away. The supermassive black hole at our galaxy's center is dormant. No gamma-ray bursts are aimed at us. No rogue planets are hurtling toward the solar system. The cosmic rays are being deflected by our magnetic field. The atmosphere is holding back the vacuum, and dark matter and dark energy, whatever they are content to shape the universe without threatening our small corner of it. The deadly objects of the universe exist, yes, but they exist elsewhere. Out there in the dark, spinning, exploding, radiating and drifting. They're part of the cosmos, essential to its structure and evolution. They create the elements we're made of, shape the galaxies we observe, and drive the expansion of space itself. Without them, the universe would be a very different and much emptier place. In a strange way, we owe our existence to these dangers. The supernovae that threaten life also seed space with the materials for new life. The black holes that destroy also help build galaxies. The cosmic rays that damage DNA also drive mutations that fuel evolution. The universe is not malicious, but neither is it benevolent. It simply is, following the laws of physics, playing out the consequences of initial conditions set in motion nearly 14 billion years ago. And in that vast, indifferent cosmos, life appeared. Not because the universe intended it, but because the conditions, however briefly and locally, allowed it. We are, in a very real sense, a fortunate accident, a small eddy in the flow of entropy, a temporary complexity in a universe trending towards simplicity. And that's okay. It doesn't diminish our existence to acknowledge its contingency. If anything, it makes it more precious. We're here, against the odds, sheltered by distance and time and the protective layers of our planet. We can look out at the deadly objects of the universe, study them, learn from them, and appreciate them from afar. And when we're done, we can return to our lives, to the warmth and safety of our world, knowing that the dangers are real but distant, possible but not imminent. So as sleep begins to pull you under, as your breathing slows and your thoughts drift, take comfort in this. The universe is vast and dangerous, but it's also vast and empty. The deadly objects are out there, but they're far away. Earth has been here for billions of years and will be here for billions more. Life has survived worse than anything we face today, and it will continue to survive, adapt, and evolve. You're safe. Right now, in this moment, you're protected by an atmosphere, a magnetic field, and the simple fact of distance. The pulsars spin, the black holes consume, the gamma ray bursts flash, and the universe expands, but none of it touches you here. Not tonight. Tonight you can let go, release the day, and drift into sleep, knowing that the deadly objects of the universe are exactly where they should be, out there, in the dark, far from here. And maybe, just maybe, that's the most comforting thought of all. The universe has its dangers, but it also has its safe harbours, and we've found one. For now, and for a long time to come, we're home, we're safe, and we can rest. The stars shine on, distant and cold. The galaxies turn, slow and majestic. And here, on this small blue world, under a blanket of air, you sleep, sheltered and safe, while the cosmos continues its ancient, eternal dance. The deadly objects remain, as they always have, as they always will. But tonight, they're just stories. Just distant lights in the dark, just part of the vast, beautiful, terrifying universe that we're so fortunate to call home. Sleep well,